Hey guys, so today we're gonna do this question. So this question is gonna be about we have a multivariate logistic regression problem. Recall that given a vector x from R of D and the parameters matrix, which is this one, so is a matrix from D of C, so D rows and C columns, where C is the number of classes. The model can be written as the following manner using the softmax function. So this is the softmax function, and now we have z. Z is w transpose times x. Now we need to show that the softmax is always equal softmax function, even if we add m for like a constant vector, for example, like this one, m. Okay, and they say for every scalar m, where 1 is the vector of 1's appropriate size. Okay, so this one's gonna be pretty easy. Okay, maybe even I'll add one here. So what we have is these steps. We have w, x, and the a. So I defined a just so it's clear to us. So this is the logic, meaning each one of them will be eventually a probability. So P1, P2, up to PC. The probability that this, like the item the input vector is related to this parameter, or this parameter. Okay? And eventually we're just gonna take the maximum. So we have C classes. So we have e to the power of zf, z0, e to z1, up to zn. This is my 1, but it's close to n. I cannot write. Okay, anyway. So what I did is just like wrote it as a long version, so it's clear to everyone how the softmax works. And now what I did is I compare both of them. Okay, and I want to get from here to here. So what I did was open it. So e to the power of zi plus m is actually can be written as this, because this is the rules like of exponent, and the same is written here. Now from here I can take this as a common denominator and just put it outside, and when I put it outside I can just cancel both of them really easily. So here and here, and then I have just this. So this is the same as this one, and it's proved. Okay, so now for c equal to, oh, hope I didn't delete anything. Okay, for c equal to, show that the sigmoid function is equivalent to the softmax function. So we want to show that the sigmoid is equal to this one. Okay, and just to remember, this is the sigmoid function. Okay, maybe you will see also 1 divided by 1 to the power of e minus x, like this, but they are essentially the same thing. I can show it maybe in a later video. Anyway, so we want to show they are the same. So what we are going to do, 1 second, I will push it just a little bit. Okay, so what we want to do is first define this variable z tag, which will be z1 minus z2. Okay, so I write both z1 and z2 as something of z tag. So z1 is z tag plus z2. Okay, so just we are clear, this is like the softmax we are aiming to get. Okay, so I wrote softmax of z1, and I just wrote it with z tag. So it's e to the power, I just show it from here. E to the power of z1 is e to the power of z tag, e to the power of z2. Okay, easy logarithmic rules, we just saw it in the previous section. So I open this one and I open this one, and then I can cancel this because this is a common denominator. So I will just show like the long version of how I cancel it. So now I have this divided by this, and this is exactly the sigmoid function. But just note that here we have z tag, not how it's called, not z1. But we will show they are the same. Okay, we'll show it later. So note this is the result we get, and I also show how we go into the other representation, which is this one. Okay, so this one for this representation, this one for this one. Okay, easy peasy. Now we're doing the same thing for z2. Okay, so I define z2 as z1 minus z tag, and I did the same action, and now I get the same but a little bit different function, which is the same but with minus. So minus z tag 1 plus e to the power of minus z tag, and here it's just positive. So you can see that this one and this one is the same function. The only difference is here you have a minus and here you don't have. So just zoom, hope you see it. Okay, so now we need to prove that the sigmoid of z tag equal the softmax of z1. Okay, and the same thing for the softmax of z2 equal the minus z tag of the sigmoid. Okay, so we'll first prove for z1, then for z2. So z1, okay, we wrote it, okay, and now I wrote the sigmoid, and now here is this step. So I just opened everything. So I opened z1 minus z2, and here is just like simple algebra of multiplying 1 by e to the z1 and divided by e to the z1. So this is still 1, okay? It's just easier for me. And then I just add them together and, the denominator. And now I can just take this, put it up, and this stays in its place, okay? You can also look at this as the following. Like 1 divided by e z1 plus e z2 and e z1, and because it's division, it's the inverse of multiplication. It's 1 to the power 1 multiply e z1 divided by e z2 plus e z1. So I just did this, and this prove it. So now I wrote it in Hebrew. Ochachnu, it's proved. This equal the the softmax of z1. Okay, and now we did the same things for z2. Okay, so you can just look at this. So we did the same thing for z2. We wrote the sigmoid. We opened it. We used the division. We open the common denominator. We flip it, and now we proved it. So now for C, we can use this f of x, okay? They ask us in C, just to be sure, present an alternative to the sigmoid function, which also maps from the real line to 0 to 1, interval, any valid solution is valid. Okay, so what I did is everything which is bigger than 1 or smaller than -1 will be 1 divided by x, and everything which is between 1 and 0 will be the absolute value. And of course this is true because you can sum, you can say that, for example, z1, the value, the softmax will be z1 divided by the sum of zj. Okay, and everything will be normalized. So this is also works, so easy. guys, hope you like this video. I will just let you a couple of seconds in the sections to look at everything. So I will pause this. Okay, hope you saw like the first section. Now I'll pause on the second section. Okay, hope you saw everything. And now I'll pause on the third section and a little bit from the second section. Okay guys, hope you like this video. Until next time, please like and subscribe. This really helps the channel. And bye bye.